So I'd like to start today by working through problem 1018 from the homework. So 1018 was one of the problems that I had several students ask questions about. So I think it's better if we just solve it here in class. So for 1018, we are given a shape, two-dimensional area, just like many of our other problems. And this two-dimensional area is bounded by the curve y equals h over b cubed to the power of x cubed. Now, if you already saw Monday's video, or if you came to class on Monday, then you probably already see that this problem is actually very familiar to the one that we solved on Monday, right? The one that we solved on Monday, we had a constant to the power of n times x to the power of n. So in order to solve this problem, we need to know the following. We need to know that this shape is bounded by the lines y equals 0, the line x equals b, and then the curve y equals h over b cubed times x cubed. By the way, Ryan, you are unmuted. Not sure if that's intentional or not.
Sorry.
Yeah, no, it's okay. All right, so let's just go ahead and solve this problem quickly. We want to find the moment of inertia about the y-axis for this problem. So we want to find moment of inertia about the y-axis. If we want to find the moment of inertia about the y-axis, there are several steps that we can take, right? We know that if we want to follow along the same procedure that we use for our centroids, then we may want to start by setting a differential element dA. So our differential element will have an area dA, and it will be located at some arbitrary point x, y. In other words, we're going to locate our differential element in the curve at some arbitrary point x, y. So if I were to draw my differential element, we want to find the moment of inertia about the y-axis. That means that our element will have to be a vertical element if we want this method to work. So we set our differential element dA, which is actually located at coordinates x, y in this curve. And after that, we would like to determine or find the coordinates for the centroid of this differential element, x squiggly and y squiggly. So for this differential element, we know that x squiggly, which is the x coordinate of the centroid of this differential element, is simply located at x. And then y squiggly, which is the coordinates of the y direction of the centroid of this element, simply located at y divided by 2. After that, we want to express our area dA in terms of our differential dimension. So our area dA will be expressed in terms of our differential dimension. If you look at this element, the differential dimension is dx. Therefore, we're going to express dA in terms of dx. So what do we have when we look at this element? This element, as you can see here, has a height of y and has a base of dx. And what this means is that the area of this element will be y dx. But of course, we can't really integrate this equation, because if we were to integrate, you'll know that y actually changes with respect to x in this curve. So if we're going to integrate this element, everything needs to be expressed in terms of our differential dimension dx. So I need to express this y in terms of x. And we do that with this relationship for the curve. So from the curve, we get that y equals h over b cubed times x cubed. So we get that our area is equal to h over b cubed times x cubed dx. And finally, the fourth and final step is to integrate. You know, it's the most fun part of this problem. It's the integrating part. And we know that if we're going to integrate, the moment of inertia about the y-axis is equal to the integral of x squiggly squared dx. Now, from step number 2, we know that x squiggly is just equal to x, so this will be just the integral of x squared. And then from step number 3, we know that dA is equal to h over b cubed x cubed times dx. So x squared multiplied by h over b cubed x cubed times dx. And for our limits of integration, because we're integrating along the x direction, we want all of the x points in this shape. So this shape starts at x equals 0 and ends at x equals b. That means that our limits of integration will be from 0 to b. So plugging all of that into my integral, I'm going to take out my constants just for simplicity. So I take out my constant a over h over b cubed, and I get the integral from 0 to b of x squared times x cubed, that's x to the power of 5 dx. Solving this integral, I get h over b cubed times 1 over 6x to the power of 6 evaluated from 0 to b. Now, if x equals b, then we get b to the power of 6 divided by b to the power of 3. That's just b to the power of 3 times h divided by 6. So our final answer is b to the power of 3 times h divided by 6. So pretty simple problem once we actually get the hang of our moment of inertia. But just so that we are all on the same page, are there any questions with this problem? All right, so if there aren't any questions with this problem, I do want to keep poking at this problem. And what I like to do now is I would like to find the moment of inertia about the x-axis. However, I want to find the moment of inertia about the x-axis using the parallel axis theorem. If you were in class on Monday or yesterday, you may have recalled that we did one problem where we were forced to use a vertical element to find the moment of inertia about the x-axis. And that requires us to use the parallel axis theorem. So I want to find the moment of inertia about the x-axis, but I still want to use this vertical element. Now, because I'm using this vertical element, then I cannot follow this procedure because, as you can see here, the differential dimension is parallel to my axis. And we know that if the differential dimension is parallel to your axis, this procedure does not apply. So instead, let's use a parallel axis theorem. As a reminder, along the x-axis, the parallel axis theorem tells us that the moment of inertia about the x-axis equals the area of the shape times the y-coordinate of the centroid squared plus the centroidal moment of inertia about the x-axis. That is the moment of inertia taken from the centroid of that element. So if we were to apply the parallel axis theorem to this tiny, tiny, tiny shape, then we can say, right, that for this tiny element, this very, very, very small element, we will have a very, very, very small moment of inertia. For this very, very, very small element, we're going to have a very, very, very small area. Now, the distance to the centroid of this element is actually not very small. As you can see, it's not a very small distance. It's a finite distance, which I'll just call y squiggly. But we do know that the moment of inertia about any axis will be very small, so I'll just call this dix. So what we're essentially doing is we're taking the parallel axis theorem and we're converting it into a tiny, tiny parallel axis theorem, right, for this small differential area. So if we do this, we can actually solve this problem quite easily. First off, you know that the tiny moment of inertia about the x-axis for a rectangle will be 1 over 3 base times height cubed. But let's start with the premise that we don't know that, right? Let's start with the premise that we only know the centroidal moment of inertia for a rectangle. If you look in the back of your book, you know that the centroidal moment of inertia for a rectangle, that is the moment of inertia about an axis that passes through its centroid along the x direction, is going to be 1 over 12 base times height cubed. If you don't remember this, we actually solved it in one of the examples. But again, you don't have to solve it every time because this is a very common value, the moment of inertia about a centroid for rectangles. So we do know that for this tiny, tiny, tiny rectangular shape, we can calculate its centroidal moment of inertia. So let's go ahead and do that. Now to solve this problem, I'm going to rearrange my terms just a little bit so that they look a little bit easier for me to handle. And I'll say that the moment of inertia about the x-axis, that's the differential moment of inertia, will be equal to y squiggly squared dA times di bar x. That's how I like to rearrange my term. I like to have my differential terms at the end, always at the right. So what do we have? Starting from left to right, we get y squiggly. Now, remember this differential element was placed at an arbitrary point xy in the curve, and y squiggly is the y distance to the centroid of that element. Now we already know from step number 2, we found that y squiggly was just y divided by 2. And if we didn't, you can find that yourself, right? You know that the centroid of this rectangle is at the center of the rectangle. So if the rectangle goes from 0 to y, the centroid will go from 0 to y over 2. So y squiggly here is just y divided by 2. And this value is squared. The area of this element dA, as you know, is simply y times dx. And then the centroidal moment of inertia is 1 over 12 base times height cubed. So I'm going to write 1 over 12. The base of this rectangular element is dx. The height of this rectangular element is y. Therefore, it's 1 over 12 y cubed dx. If we further solve this problem, we get that y squared times y is y cubed, and 2 squared is 4. So this will be y cubed divided by 4 dx plus y cubed divided by 12 dx. And you know that 1/4, right, plus 1/12 will give us 1/3. So we get 1/3 times y cubed dx. I know that we already knew this because the first problem we solved last week was to find the moment of inertia about our x-axis of a rectangle, and we got 1/3 base times height cubed. But even if we didn't know this, you can see that it only takes 3 steps in order to calculate the moment of inertia for this differential element. However, this is only for the differential element. And we see that we have y and we have dx. And y changes when x changes, which means that we have to express this y in terms of our x coordinate. So if we look at this curve, we see that y actually already exists in terms of x, right? Y is equal to h over b cubed times x cubed. So I can write it here. Dix simply equals 1 over 3 h over b cubed times x cubed. And y is cubed, so all this is cubed, dx. So we have dix, we have dx, and this is only the moment of inertia for a tiny rectangular element. If we want to find the moment of inertia for everything, then we need to find every single moment of inertia for every tiny element and add them up. However, instead of adding up an infinite number of elements, you know that we can integrate. So if we integrate both sides of the equation, we will get that the moment of inertia about the x-axis here will be equal to this integral. And this integral will be 1 over 3 times h cubed over b to the power of 6 times h to the power of x to the power of 6 dx. And because we're along the x-axis, let's recall our limits of integration, right? We want to make sure that we integrate from 0 to b. Quick correction. We are integrating from b cubed elevated to the power of 3, so this will not be 6, this will actually be 9. And x will be elevated to the power of 9. I almost missed that, okay? So we have this integral, and this integral you'll see is actually quite easy to solve. I'm going to take out my constants, so I'm going to take out h cubed. And I am going to take out my 1/3 and my b to the power of 9. So what's left is the integral from 0 to b of x to the power of 9 dx. As you know, solving this integral is actually quite easy. This integral will be 1 over 10 x to the power of 10 evaluated from 0 to b. So evaluating this integral gives me b to the power of 10 divided by b to the power of 9, that's just b, h cubed divided by 3 times 10, which is just 30. So my final answer should be my base times height cubed divided by 30. And that is the moment of inertia about the x-axis. So notice that we didn't have to draw another element. But even if we did draw another element, we would have still ended up with the same answer. So not much difference there. If you've already started by drawing an element, you may consider using the parallel axis theorem. So that was problem 1018. We solved it, we solved what the book was asking for, and then we solved a little bit extra just so we can get some practice with the parallel axis theorem. Up to this point, are there any questions with this problem?
Is this being recorded and will this be posted and available tonight?
Not tonight.
Okay. I'm just having a little bit of lag on my end, but I'm sure later when I get home it'll be fine.
Okay.
All right. I know that that's not pertaining to the question.
Yeah, it's okay.
Specifically,
so, yeah, it is recorded, but not. I don't think I'll be able to post it tonight. You may be able to see it tomorrow in the afternoon.
Okay, that's fine. Thank you.
Okay. So, as far as this problem goes, I think we have a good idea of how to solve these problems by using our standard method and by using the parallel axis theorem. On Monday, one of the students asked me to go over some composite area problems. So I'd like to try that now. I'd like to go over some composite area problems. So we're going to solve from our books problems 1025 and 10-26. So I'm going to try to find them in my book first so we can solve them. All right, so let's solve problems 10-25 and 10-26. This is a composite moment of inertia. So we're dealing with an area that is a composite area. And these, again, should be relatively easy to solve once we actually understand how to calculate the moment of inertia. So what we have here is 10-25. And for this problem, 10-25, we are given the following shapes. So we have here is a composite area, right? It's an area where we don't really have one equation describing this curve. Instead, what we can do is split this up into more well-known areas. Our dimensions are 3 inches, 3 inches, and 3 inches. Before I go any further, Ryan, I think you were there on Monday. Did we solve this problem on Monday?
No, we did not. I think Noah asked that. He asked about that one.
Okay, good. So let's just go ahead and solve this one. I just want to make sure I'm not repeating any problems. Because I think we did solve it on Tuesday, but I didn't record Tuesday's lecture. Good. So we would like to find for 1025 the moment of inertia about the x-axis, and for 1026 the moment of inertia about the y-axis. So let's start with the x-axis, right? What we have here is a composite shape. And what I mean by composite shape is an irregular shape that can be reduced or divided into simple or easy to calculate shapes. So if we look at this composite shape, can you think of any regular or simpler shapes to divide this into?
You could do the 3x3 triangle, and then the 6x6 triangle, and then the rectangle, which would be 3 and 3.
That's absolutely
3 by
right.
3.
We can divide this into two triangles and a rectangle. So I can divide my area, and I am going to number them so that I can keep track of my results, 1, 2, and 3. And if I want to find the moment of inertia for this composite area, let's recall that the moment of inertia for a composite area is simply equal to the sum of the moment of inertia for the individual areas. In other words, Ix is just equal to the sum of Ix for each of these elements. Now, one way to solve this problem is by looking at known values. And for triangles and rectangles, we already know the moment of inertia about the centroid of that axis. And we can use that and the parallel axis theorem to find the moment of inertia about the x-axis. So if you look in the back of your book, you can find the moment of inertia about the centroidal axis for triangles and for rectangles. In other words, we're going to try to find moments of inertia about an axis that passes through the centroid for this triangle, through the centroid for this rectangle, and through the centroid for this triangle. So if you have your book with you, do you know what the moment of inertia for the centroidal axis for each of these triangles is? And let's start with triangle number 1. Triangle number 1, we get that the moment of inertia about the centroidal axis is what for a triangle? And this will be on the last page of your book, on the back cover of your book.
I think it's 1/36 base times height to the third.
That's correct. 1/36 base times height to the third. So for this triangle, we can see that the base is 3 inches. The height is 3 inches. So it'll be 1/36. 3, that's the base, times 3 to the power of 3, that's the height. So we get 3 times 3 times 3 times 3 over 36, 3 to the power of 4 over 36. And how much is that?
Three-fourths.
3/4? Okay. So 0.75 inches to the power of 4. All right, good. Now this is just a moment of inertia about the centroidal axis. If we want to translate this moment of inertia into the moment of inertia about the x-axis, we apply the parallel axis theorem. Remember, the parallel axis theorem tells us that the moment of inertia about the x-axis equals the area times the distance to the centroid squared plus the centroidal moment of inertia. So what do we have? For this triangle, my area is base times height over 2. So 1/2, 3 times 3. The distance to the centroid is the distance from the x-axis to the centroid of this triangle. Now for triangles, you know the centroid is at 1/3 of the length of the distance measured from the base. So if this triangle has an altitude of 3 inches, the centroid will be located at 1/3 of those 3 inches, which is 1 inch. But we want the distance from the x-axis to the centroid. So from the x-axis, we have 3 inches plus 1 inch. That's a total of 4 inches. And remember that that distance is squared. And to that we add the centroidal moment of inertia, so 0.75 inches to the power of 4. Solving this gives us the moment of inertia about the x-axis for this triangle, and this only for the first triangle. I have my calculator with me, so I'm going to try to solve this. I do want to make a correction to your answer here, Ryan. When I calculated, I actually get a moment of inertia of 2.25 inches to the power of 4. So let's just double check our calculations here. So we get 2.25.
Yeah, I missed a 3.
Okay, so 2.25, and here 2.25. All right, and then plugging in everything else, we get 1/2 times 3 times 3 times 4 squared. So that's 16 times 9 divided by 2. And to that, we add 2.25, and we get a moment of inertia of 74.25 inches to the power of 4. And you can see that this makes actually a big difference. This distance from the centroid actually makes a really, really big difference when it comes to the moment of inertia. You see it increases a lot, right? Even though we're just moving it about 4 inches away. So keeping that in mind, we have our moment of inertia about the centroidal x-axis for our first element. Our second element is a rectangle. And because it is a rectangle, it should be a little bit easier to solve. We know that the moment of inertia about the centroidal axis for a rectangle, we used it earlier, was 1/12 base times height cubed. The base of this rectangle is 3 inches.
Isn't the moment of inertia 74.25?
74? Oh, my bad.
I think you had that on your calculator, but...
Okay, so 74.25, right? Yeah, I think it should be, right? 16 times 4.5 is 72. Yep, and then plus 2.25 is 74. Good, thank you. So for the rectangle, we get that the moment of inertia about the centroidal axis is 1/12 base, which is 3, times height cubed, and the height is 3. So we get 3 to the power of 3. Oops, 3 to the power of 4, which is 81. And then divided by 12 gives us 6.75 inches to the power of 4. Applying the parallel axis theorem once again gives us that the moment of inertia about the x-axis is equal to the area times the distance to the centroid squared plus the centroidal moment of inertia. For this rectangle, my area is 3 inches times 3 inches. And the centroid is located at 1.5 inches from the x-axis. Remember, the centroid of a rectangle is located at half of the distance of that rectangle. So that would be 1.5 inches. And to that, I add my centroidal moment of inertia of 6.75. This gives me a moment of inertia about the x-axis of 3 times 3 times 1.5 squared plus 6.75. We get a moment of inertia of 27 inches to the power of 4. I think this one was relatively easy because we already had solved the centroidal moment of inertia for a rectangle. But now we'll do what's left, right? Which is to find the properties for the bigger triangular section. So for that larger triangular section, we know that the centroidal moment of inertia is 1/36 base times height cubed. And for this triangular section, the base is 6, the height is 6. So we get 6 times 6 cubed. Punching these numbers, we get 36. Let me just confirm. Yep, 36 inches to the power of 4. And then we apply the parallel axis theorem to transfer that moment of inertia to the moment of inertia about the x-axis. The area of this triangle is 1/2 base times height, so 6 times 6 divided by 2. The distance to the centroid is going to be 1/3 of the altitude. In this case, 1/3 of 6. So 6 divided by 3 is 2 inches. And then to that, we add the centroidal moment of inertia of 36 inches to the power of 4. Solving this, I get 36 times 2 plus 36, 108. So at this point, we found the moment of inertia about the x-axis for all of these different shapes. So before we solve for the composite moment of inertia, are there any questions?
No, sir, not on my end.
All right, good. In that case, let's just go ahead and finish solving. Let's just do a final spot check. We get 1/36 base times height cubed. That's correct. 1/2 base times height times the distance to the centroid squared. For the rectangle, we get 1/12 base times height cubed. We get base times height times the distance to the centroid squared. That's correct. And then for here, we get 1/36 base times height cubed. And here we have area, which is base times height over 2 times the distance to the centroid squared. Good. It looks like we have what we need. So now we can calculate the moment of inertia about the x-axis, which is actually the sum of all the moments of inertia about the x-axis for our 3 little shapes. So I get that this will be 74.25 plus 27 plus 108. So adding them up, I get 209.25. I'll just round to 209 inches to the power of 4. And that is the moment of inertia about the x-axis for a composite section. On problem 10-26, which we can actually solve right here, we're asked to find the moment of inertia about the y-axis. And you'll see the procedure is actually the same, right? We want to find the moment of inertia about the y-axis, and we do it by dividing this shape into 3 regular shapes. Again, 2 triangles, 1 square. Now, our centroidal moments of inertia are going to pass through the centroid. However, they will be oriented to be parallel to the y-axis. So I'm going to try to speed through this one because it is something that I think we're already familiar with and we know how to solve. For our first triangle, the moment of inertia about the x-axis, about the y-axis, can be found with the parallel axis theorem. And the parallel axis theorem tells us that the moment of inertia will be equal to the area times the distance to the centroid squared times the centroidal moment of inertia about the y-axis. So for this triangle, my area, once again, is 1/2 base times height. My distance to the centroid is the distance from the y-axis to the centroid of this element. Notice that this triangle starts with the little side and ends with the base. So the distance will be 2/3 of your base. So 2/3 of 3 is simply 2. To this, we need to add the moment of inertia about the centroidal axis. So for my centroidal axis, we know that for a triangle, the moment of inertia about the x-axis is 1 over 36, 3 a base times height cubed. However, here we have a little bit of a problem, right? For the centroidal axis, we need to understand that our axis is not going to be oriented in this direction, right? It's not going to be oriented parallel to the base. It's actually going to be oriented perpendicular to the base. So if my centroidal axis is oriented perpendicular to the base, then how do you think the centroidal moment of inertia will look like if my centroidal axis is oriented perpendicular to the base? Instead of 1 over 36 base times height cubed, what do you think it will be?
One over 36 height times base to the third.
That's correct, right? So my centroidal axis is oriented in the other direction. These two dimensions are switched. Now, for this triangle, it doesn't really matter because my base and my height are the same, but I just want to make sure that we understand that in this case, the centroidal moment of inertia is 1 over 36 base cubed times height, not base times height cubed. Good. So we find the moment of inertia about the y-axis. Now, I'm going to let you calculate yourself, and I'm just going to calculate for the rectangle. For the rectangle, moment of inertia about the y-axis is area times distance to the centroid squared times the centroidal moment of inertia. My area is base times height. That's 3 times 3. The distance to the centroid is 1/2 of 3, so that's 1.5. And then the centroidal moment of inertia is 1 over 12 base cubed times height. So 1 over 12, 3 cubed times 3. And that I can let you calculate as well. For the other triangle, we have the same thing. Moment of inertia about the y-axis is area times distance to the centroid squared plus centroidal moment of inertia. For the final triangle, we know that the area of that triangle is 1/2 base times height. And then the distance to the centroid is going to be the distance between the y-axis and the centroid of this triangle. Now we know that the center of the triangle in the y direction will be at 1/3 of 6, which is 2 inches. However, we want the distance from this axis. So from this axis, we get 3 inches plus 1/3 of 6 inches. Okay, so 3 inches plus 2 inches. My distance to the center will be 5 inches. And to that, we need to add the centroidal moment of inertia, which we already know is 1 over 36 base cubed times height. I mentioned that at this point, you can calculate these values yourself. I wanted to make sure we have everything done before we calculate, but no, let's go ahead and calculate everything. We get that for our first triangle. We have 1/2 3 times 3 times 2 to the power of 2 plus 1 over 36 3 to the power of 4. I get 20.25 for the first triangle. And if you have a different number, feel free to correct me. For the rectangle, I have 1.5 squared times 9 plus 1 over 12, 3 to the power of 4. I get 27. Inches to the power of 4. And for my last triangle, I get 1/2 6 times 6 times 25 plus 6 to the power of 4 over 36. 486. So finally, to get my moment of inertia about the y-axis, all I have to do is add up all these numbers. So I get 20.25 plus 27 plus 486. Which gives me 533. And that's it. That is how we calculate moment of inertia about the x and the y axes for this composite section. So at this point, are there any questions? All right, good. If there are no questions, I think this is pretty much the material that I was hoping to cover for this chapter. So with the time we have left, we can either close early, or if you have any problems that you would like for me to solve, maybe some problems that you had some issues with or that you don't understand how to solve them, just let me know now so we can go over them with whatever time is left in this class.
I'm still at work. I was just waiting until the meeting was over, so I'm probably going to go ahead and head out. Thank you for your time tonight.
Yeah, no problem. Thank you, Paul.
Just a quick question on 1028. It has the rounded edges, but can you still cut it off as rectangles?
For 1028, so they
Yeah.
didn't give us any radius of those rounded edges, right?
Correct.
So just assume it's a rectangle. I think, and let me just show it here so that the other students know what you're talking about. If they don't give us any radius of these edges, then we really can't do anything with that. We'll just have to assume it's rectangular.
Okay. All right.
Okay. Any other questions or any other problems that you may want me to solve?
I have no questions.
1051 is kind of interesting too. It's got like a trapezoid
All
and
right.
angles and stuff.
Okay, let's solve it. 1051, right?
Yep. Yes, sir.
Okay. Let me look for it in my book. All right, so let's look at 10-51. That is a pretty interesting one. I'm actually going to need to look at the book closely so I can draw it correctly. All right, so 10-51, we have this interesting shape. That looks something like this. Ugh. Imagine that it's symmetrical about its center. So this is our cross-sectional area for 10-51. And we're giving several measurements. So I'm going to write them down. So for 10-51, we're told that we have 100 millimeters from the center to each of the sides. This circular shape is actually an arc of a circle. It's actually the arc of a circle with a radius of 200 millimeters. So if we were to draw a circle with a radius of 200 millimeters, that arc would be this shape, so 200 millimeters. And then that arc would be defined as going from angles from the center, 45 degrees in each direction. And this circle is going to be the same. So that this actually is symmetrical. I don't want to have to draw it again. The thickness on both the top and the bottom is 25 millimeters. So this is actually symmetrical about its center, about an axis that's horizontal and a vertical axis, okay? Good. So for this problem, we are asked to determine the moment of inertia for this cross-sectional area about the centroidal x-axis. That is an x-axis that passes through the centroid of the cross-section. So if I were to draw my centroidal x-axis, I know from the symmetry here that the centroid is here at the center. My centroidal x-axis will be the axis that passes through that centroid. Okay? And I want to find the moment of inertia. Now, of course, this is a good example of a composite area because you can see that there are several more or less very well-defined areas here. Now, the question is, how do we want to split this, right? Because we're going to have to choose a correct way, I would say, of splitting this element, all right? So any ideas? Looking at this element, looking at everything, all of its features, how do you think we would be able to split this element to find that centroidal moment of inertia?
Could you make a rectangle on the top and then one on the bottom and then a third one, and then you make two circles and then you cut the two circles out?
Okay, so we're looking at a rectangle on the top, rectangle on the bottom, a third rectangle, and then two circles.
Yeah, I'm not really sure how you gotta do something to cut the curve out.
So let's remember one thing, right? Let's remember that we want to split this, right? We want to divide this into areas that we can recognize, right? So rectangles, triangles, circles, but not much else, okay? Perhaps wedges of circles if necessary, but really not much else. So if you're not sure what areas are appropriate for you to split this, go to the back of your book on the geometric properties of line and area elements table. And if you look at this page in the book, you'll have common areas that you can divide this into. So look at this shape and then look at the areas included in this table. The ones that you can't see on the video are, well, a triangular and a parabolic area. But if you look at these areas right now, is there anything that you think you can more or less use? I think you're on a good spot right now when you said rectangle. I think rectangle is definitely one of the shapes that we want to use. But what other shapes do you think we can use for this element?
A semicircle?
I would go a little bit more.
Oh wait,
detailed,
circular
right?
sector area. I think it was at the top.
All right, yeah,
Circular,
a wedge, right? That's correct. Yeah, we want to make sure that we have a wedge. But we have a problem here, right? If we do use a wedge, we're going to be counting or discounting more than what we need, right? So here's what we're going to do. And hopefully this will allow us to understand a little bit better how composite moments of inertia work. You may recall that when we had an area, such as a rectangle with a hole cut into it, we would calculate the moment of inertia of the rectangle, and then we would calculate the moment of inertia of the circle that forms that hole, right? However, we would subtract that moment of inertia of the circle. Why? Because the circle actually isn't part of this element, okay? Now, I want to use that logic. I want to follow that logic in order to look at this element and decide how to split it. First off, Ryan, you mentioned rectangle. I don't think it's necessary to do 3 rectangles. I think we can actually just do 1 full rectangle. So let's start there. Let's start by choosing to divide this shape into different shapes. And one of those shapes is going to be my rectangle, okay? So then what is that rectangle, right? So if I look at what I have right now, okay, how or where do you think I would be able to use that rectangle?
Could you just go straight from the top left to the bottom right?
Okay, so pretty much a rectangle that covers everything in that shape. Is that what you're saying?
I think that's how you would do it.
All right, good. So let's look at that and let's see if that works. Okay, so I want to start under the assumption that we're not really sure what the answer is going to be. So let's see if that works. Okay. By the way, this is an interesting problem because you can split it up in a number of different ways and still land the same answer. All right. So is this what you're saying? A rectangle that covers everything?
Yes.
Okay. All right. So we split it up into this rectangle that covers everything. However, this will give us a greater, right, a higher moment of inertia than what we really want, right? Because we are including a section that really isn't there. So then how could we perhaps modify this rectangle, add or subtract elements so that it starts to look a little bit more like our shape?
Or I guess if you cut the two wedges out, if we're doing that still.
Okay. So we're going to cut the two wedges out. So that means that we're going to remove this section, right?
Are you pointing at stuff right now or like drawing stuff?
Yeah, is it not showing up?
No. That's weird. Looks like it's frozen. Might just be me. I can join back.
Yeah, let's try that and see if it works.
Okay, I can see it now. It might have been me.
Okay.
Sorry about that.
No problem. All right, so we want the moment of inertia about this centroidal x-axis. And then what are we left with? We have our wedge, and you mentioned that we can remove this wedge. Is that correct? Because if
Yes.
we remove the wedge, we're going to get rid of this area that we didn't need, right? So we can remove the wedge. But notice that by removing the wedge, in addition to removing this area we don't need, which gives us the shape that we want, we're also removing a lot more that we do need, right?
Oh, yeah.
So when we're removing the moment of inertia about the wedge, we need to consider that in addition to doing that, we're going to have to perhaps add the stuff that we removed, the portion that we removed. So what do you think can be done about this? How do you think we can solve it? So we removed not just the moment of inertia about the wedge, but we also removed all this moment of inertia. And let me draw the other wedge as well, so that we know what we're doing. We've removed this, but also we've removed this. One rectangle, two rectangles. So what can we do? What do you think? If we remove the moment of inertia from this element, what do you think we could do to make up for it?
Could you just add the two moment of inertias of the two triangles?
Exactly, right? We can add the moment of inertia about the centroidal x-axis of a triangle. So we can add the moment of inertia about a triangle. Now, if you look at your book actually gives you centroidal moments of inertia if the base is parallel to that centroidal axis. So what we can do, because the triangles are symmetrical, we can add the moment of inertia for 4 of these triangles. All right? I think that's a good way of splitting this up. Again, there's different ways that you can split up this problem. But as long as I would say as long as you know what you're doing, you should be able to get the correct the correct answer here, okay? So if this is how we're gonna split it, then let's do it, but we need to find some dimensions in order to solve this problem. So what we're doing here is we have this rectangle, we're gonna get the moment of inertia for this rectangle. We're gonna subtract the moment of inertia for 2 wedges, but that's also gonna subtract a little bit more. So we're gonna add back the moment of inertia for these 4 right triangles, and that should give us the moment of inertia for this composite shape. So I'm gonna start with the rectangle, okay? So if we have this rectangle, I'm gonna call this my number 1, my shape number 2, which is twice, and my shape number 3. So starting with shape number 1, we have this rectangle. And what are the dimensions for this rectangle? We know that in the base, we have 100 plus 100, it's 200 millimeters. And we're gonna have to use some geometry to calculate the height. We know that the radius of the circle is 200. And if the radius of the circle is 200, then this distance should be 200 times sine of 45. We know that this distance is 25, and this distance is 25. I'm going to write down my distances here. I have from here to here, I have 25. And then up to this point, I have 200 times sine of 45. And of course, symmetrical in the bottom half. So if I add these terms up, I get 332.8 millimeters. I'm just going to round to 333, but you don't round until you do your calculations. Good. So we found this rectangle, we found the base, and we found the height. What is the moment of inertia about the centroidal axis for this rectangle? We know that about for the centroidal axis of this rectangle, the moment of inertia is 1 over 12 base times height cubed. So 1 over 12, my base, which is 200, my height, which is 332.8 cubed. This gives me 614562289. It's a little bit of a big number, but 614,562,289 millimeters to the fourth. That's my moment of inertia about the centroidal axis. Now my question, Ryan, would be, is the centroid of this rectangle, does it coincide with the centroid of the shape?
Yes.
Okay, so there's no transformation needed, right? We'll apply the parallel axis theorem. We get that Ix is simply a y bar squared, but y bar squared is 0. So this will just be equal to the centroidal moment of inertia. No transformation needed. Okay. So now we can turn to our wedge, shape number 2. So what do we have for our wedge? We have a wedge. And I would say we can start, in order to know which dimensions we need to look at, let's find the equation for the moment of inertia about the centroidal axis. For this wedge, okay, the centroid is at the center of the wedge, which actually coincides. So for this wedge, The moment of inertia about the centroidal x-axis is 1 over 4, radius to the power of 4 times theta minus 1/2 sine of 2 theta. So I'm going to write it down. The centroidal axis moment of inertia is 1 over 4, radius to the power of 4 times theta minus 1/2 sine of 2 theta. And the reason I'm writing this down first is so that I can actually know what I need to find. So notice that I need the radius, and we know the radius is 200 millimeters. And here theta, right? We need to be a little bit careful. Theta represents the angle from the x-axis to that radius. So theta is not the entire angle of the wedge. Theta is actually half of that angle of the wedge. So theta is just 1/2 of the angle of the wedge, which we already know to be 45 degrees. So we can now find the moment of inertia about the centroidal axis, 1 over 4. My radius is 200 to the power of 4. Be careful here. 45 degrees has units that do not match any of this, right? So we need to apply this into a dimension, or write down our angle as a dimensionless number. So degrees have dimensions, right? Degrees, they have units. But there is a way we express angles that doesn't have dimensions, and that's radians. So 45 degrees, how much is that in radians?
Pi over 4.
Pi over 4, that's correct. Minus 1/2 sine of 2 theta. In this case, 2 theta is just 90 degrees. And sine of 90 degrees is just 1. So we plug these numbers in. What does this give us? Let me start with the pi over 4 plus, or minus, my bad, minus 1/2 sine of 90. And sine of 90 degrees is just 1. So minus 1/2 times 200 to the power of 4. Then divided by 4. And that gives us 114159265. So 114 million. Up to this point, is everything we're doing making sense, or do you have any questions?
I'm good now. As soon as we got past that wedge thing.
Yeah. I think, yeah, as long as you know how to divide this up, and you know you can subtract and add as much as possible until you land at your shape, right? The triangle should be relatively easy, as you know. We need some dimensions. We know that this is 200 millimeters, and this is 45 degrees. That means that this distance will be 200 times sine of 45. This distance will be 200 times cosine of 45, but they're both the same. So 200 times sine of 45 is just 141.2, which is the same as the cosine. And then moment of inertia about the centroidal axis for this triangle is 1 over 36 base times height cubed. Which is 111,111,11. So 11,111,111. And let me not forget my units, millimeters to the power of 4. Now, there's a problem here, Ryan. Can you identify that problem?
Well, you have them in, so there's 4 triangles, but they're all in different parts. I mean, they're all in different places compared to the middle. Or the
Exactly. So we do need to apply a correction here. Now, the good thing is that the centroidal axis for these four triangles is actually at an equal distance from the centroid here, right? Because they're both going to be at 1/3 of this distance, 1/3 of this distance, 1/3, 1/3, which is all the same. But we still need to apply a correction, right? We need to apply a correction to find the moment of inertia about the x-axis for this triangle. So we know that the parallel axis theorem tells me that the moment of inertia about the x-axis is a y bar squared plus I bar x. And for this triangle, my area is going to be 1/2 base times height. The distance to the centroid is 1/3 of this distance. Okay, so it'll be 1/3 of 141.2. And of course, this is all squared. And to this, we're going to add our centroidal moment of inertia. I'm running out of paper space here, and since we're almost done, I don't want to have to use a new sheet of paper. So I'm just going to plug in all these values into my calculator to solve it. See, I got 141.2. I'll just do the whole thing without rounding.
What was the y bar again for that? It would be 1/3 of 200 sine 45.
Yep.
Okay.
So 1/3 of 141.2. 141.4. Oh, I keep writing. I was writing 2. I should have written 4 here. Thankfully, I didn't round in my I didn't round the calculator, so we're not going to have that issues here, but it should be 4. So we'll get 141.4 to the power of 2 to the power of 3 to the power of 4. Divided by 2, divided by 3, and then plus my moment of inertia by the central axis, which is 11,111,111.11. We get 777,777,777.77 and so on. So that's 77,777,777.77 millimeters to the 4th. Got a new pen and the ink is not working very well. Okay. Finally, and again, I ran out of space, so I'm going to have to write it somewhere here. Finally, we can calculate our moment of inertia about the centroidal x-axis for this shape. And that will be the sum of all the moments of inertia. Remember that we have one rectangle, but we have 2 wedges and 4 triangles. So we have the moment of inertia of my rectangle, that's 614 million. I'm going to do 614.6 times 10 to the 6 minus twice the moment of inertia of the wedge. So it's 114 million. Plus 4 times the moment of inertia of the triangle. So that's 77.8 times 10 to the 6 and multiplied by 4. I'm gonna round. So I'm gonna round just because I haven't kept track of all these numbers. So 614.6 minus 2 times 114.2 plus 4 times 77.8 gives me 697.4 times 10 to the power of 6 millimeters to the fourth. We could have done some rounding errors. So let's make sure that everything is actually correct. But it seems like this is what we got. Anyway, up to this point with this whole procedure, are there any questions?
Nope, I think I'm good.
Great.
Thank you for doing this one. There's no way I would have been able to do this.
No problem. I'm gonna recommend that we double check our math, make sure the math is correct when we actually solve this. I'm getting a slightly different answer from the book, but other than that, I think the procedure is correct, definitely. In fact, if you look at the solution that the book presents, everything here is on the solution. So it could be that there's some error in my numbers here or in my calculator, or my calculation. But yeah, and look at that, we finished just in time for class to end. So I guess I will see you next week.